Okay, so now what I am going to show you is a demonstration setup from our lab colleagues. Ms. Madhuri has been working on this. So what I have here is a RFDC electronics. This is the RFDC board, this is the RFDC board. RFDC energy, you take RF energy, convert it into DC and store in this capacitor, okay, you store in this capacitor. And how are you throwing RF energy on this, how are you powering this, how are you feeding RF power? You are feeding the RF power through this antenna. The antenna is here, you can see, and which is the RF source? Well, the RF source is right here. This is an RFID reader. This RFID reader is a handheld reader, it is a portable reader, and this reader is actually connected to this mobile phone through the audio port. This is called Arete Pop EM reader, and it is throwing plus 25 dBm of transmission power. As you can see, the range is very short. You still have to apply the path loss for this distance and then calculate the received power. We can do that at a later time, but you can already use the Fry's equation to find out what is the actual received power here. This antenna is tuned for the sub 1 gigahertz 850 megahertz because 850 is indeed the RFID frequency. And you can also see that this board has a little piece of electronics here, small circuitry here, which is essentially the impedance matching, right. We did discuss about the maximum power point tracking, which would be required in order to maximize the amount of energy for improving the efficiency of the system. Therefore, you do have the impedance matching circuit, and once the impedance is matched, it is fed to this board, and this indeed is the RFDC board. And at the end you get DC, which is here, and what do you do with this DC? Well, once you get sufficient amount of DC, you actually power this little board. This board I will perhaps twist and show you. This is essentially a microcontroller board. This is a small microcontroller board which is connected through this gateway device here. Okay, let us see how good this system is doing. So I will ask Madhuri to hold against the capacitor, and let us now focus on the multimeter. You can see now that the multimeter is reading 3.66, and slowly you will see that it will increase to 3.67. So let me not load the capacitor, and we will only make intermittent measurements so that we can actually show you that it is building. So what should happen? Soon as it builds to a little over 4 volts, you will see a data packet on this mobile phone, okay. So that is another important thing. Right now you can see that there is no data packet, there is nothing here, it is blank, and so we need to ensure that, yeah, now let us see how much is the voltage. It is 3.74, it is 3.74, so we will have to wait a little longer. Alright, very good. So what is important is it should be in this scanning mode. If you press that, it will stop scanning, so it is continuing to scan. This is a simple Android app given by the manufacturer of this device, which allows you, which actually tells you that it has received a data packet. Now the communication from this controller board is Bluetooth low energy. This is the Nordic NRF board, which essentially is an SoC which has the BLE radio built inside the system, and you should be able to power the board, and you can see that it has built significantly well, and you can see the success here that we do have a data packet which you see here, this is indeed the data packet which has come. So what is the summary of this experiment? The summary is that if you have a sensor node which is connected to the which essentially has RFID, essentially which has a sensor connected to this board, and it does not have any battery. You want to come and let us say come with a handheld reader like this, and you want to power this sensor node. Let me, now that the demo is over, you want to power, this is just a lab demonstration setup which makes things a little more modular. That is why we have a passive board which connects this. So you could essentially come, this is let us say your electronics, and with the sensor you come periodically and try and see if you want to read the sensor value through that. You just come close to this and then you get the sensor value, right. Many such applications are possible where you want to sense through on the fly, you want to sense some amount of without a battery. This is basically a batteryless system which allows you to gives you the flexibility to read sensor value if without battery and on demand. Whenever you want, you go there, take the system, power it with the you basically power it with the RFID reader, and basically power the system here, power the system with the reader, and then you essentially read off the sensor value. How did this work? Can you build this all by yourself? What is the magic behind this powering and transmission? I will show you that in a moment. Essentially what we have here is this circuit. You can see that this is the antenna, okay, that is nothing but this antenna, right. This is the antenna here, essentially this is the antenna here, and this is a Dixon charge pump. This is nothing but a Dixon charge pump. Remember we discussed this Dixon charge pump, multi-stage, 1, 2, 3 stages of Dixon charge pump. All the energy coming from the RF is multiplied, voltage multiplier here, Dixon voltage multiplier circuit, and stores that energy in this tantalum capacitor. Now this is an LDO TPS 678001 LDO from TI, another one, some vendor, and one vendor from where we could get this regulator LDO, and the output is essentially giving you a certain fixed value, right. As you can see, if you use an LDO, you will have to put the stability capacitors. This is the C8, which is a stability capacitor, and this is the input capacitor. This is the capacitor on which there is a storage, and you can easily build this multi-stage Dixon voltage multiplier. I will give you some details of this voltage multiplier, where you can buy this IC, where should you buy it, and how you can actually use it. So let us go back to this part here, where you can actually source this from DigiKey easily. You can easily source this component from DigiKey. This is RF diodes, it is an RF diode nothing but a Schottky, it is a Schottky, Schottky RF diode. These are also called detector diodes. This is from a company called Avago. Okay. The diode that I have used in our lab is HSMS 2852, most suitable for the sub gigahertz frequencies, because we used the RFID frequency of 850 megahertz. This is the RFID frequency, and therefore these diodes are quite suitable for application. Build your voltage divider circuit, voltage multiplier circuit, Dixon charge pump voltage multiplier, Dixon voltage multiplier circuit, and then connect it, and essentially you have to build this. So let us take a very practical circuit and see if we can actually rig up this circuit and show you this voltage doubler output. Okay. For this, let me put back this picture to you. I just quickly redrew that. You have a microcontroller and there is a GPIO pin on the microcontroller, and to this microcontroller what I will do is I will connect to one of the pins. I will connect the Schottky diodes. These are basically Schottky diodes. You can look up BAT54 diodes, which are essentially Schottky diodes, and this is the arrangement. You have a diode here and you have a capacitor here, and you generate a clock here, right. Basically a small clock circuit generated here. This clock frequency is a critical thing. So what should be the clock frequency is another story. We will come to that in a moment, and I will tell you the design requirement for that. Then you are essentially trying to get an output voltage here. Okay, so this is the output voltage, V out is here, and for that what you do is you have this arrangement, and the output capacitor is connected here. The second the stage of the diode, the actual doubler circuit part comprises of this circuit, and the load RL is connected here. Now if you look at the, if I draw your attention to what I have shown here, you have 2.9 volts connected to this input, okay, where that is essentially what is being fed to this diode, and it is charging this capacitor. Okay, it is a DC that is being fed to the capacitor, and there is a clock. Right now the clock frequency that has been set for this demonstration is 20 milliseconds. That means it is a 50 hertz clock, and so it is just clocking, and what is appearing across this capacitor here is appearing doubled across this capacitor. That is all that is happening. And why is that happening? Because of the doubling action. 0 is here, 2.9 volts is here, and then automatically 5.2 volts will appear here. Okay, it is the reason why it is not really, ideally it should be double, but it is not, practically it is not, because of these two diode drops, and the equation for that is here, a very simple equation. 2 times V in is what you expect, V in is here, V out should be, this is V out. So let me write it carefully here, this is V out, V out should be 2 times V in minus 2 diode drops which occur here, which is roughly 5.2 volts. Now the value of this capacitor will largely depend on the current that you want to draw, right, the power that you want to draw through the load resistor. So it should be able to give you whatever energy that is there, which is half CV square, right. It should be able to source that for whatever duration of time that current is required. It should be able to, the power that is required will have to be sourced through the value of that capacitor. So the capacitor value will be determined based on the power requirement of this RL. Also the clock frequency is critical, because every time the power is drawn, the voltage across the capacitor is going to fall and then again going to rise when the power is reduced, right. If you want to reduce this ripple and make it even more shorter, let us say smaller ripple, then you obviously have to increase the frequency, switching frequency, that is the key here. So, the choice of switching frequency will largely depend on what is the kind of ripple that your system can tolerate. Okay. So, keep these 2 points in mind, and let us now move on to see an actual demonstration which Ms. Madhuri and Ms. Anuja have set together. We will actually show you through a multimeter the values at this point. You will see an input of 2.9 which they will show you, and they will show you an output which will be close to 5.2 volts. And for that what they have done is they have taken a standard microcontroller board, and that microcontroller board is being powered through some USB system, but what actually is available on this pin is actually 2.9 volts. So, let us now go to the demonstration and see whether we are able to set up this circuit. The value of the capacitor that they have chosen is 33 microfarad, 33 microfarad for both the stages, for this at this value as well as this value. As I said, the value of the capacitor will largely depend on the power requirement of your output load. Okay. And these are BAT54 diodes. You can connect any potentiometer that is required at the output, keep varying this potentiometer to understand across variable loads what kind of current you can actually draw from the system and see whether it matches the load requirement. So, as simple as this can easily be built. These essentially it is a Dixon voltage doubler that you have that we will be putting together. Many situations will come where there will be a microcontroller, there will be some other peripheral, something like a display unit, and this display unit will require a higher voltage as compared to what is available on the board. So, that is the time when you actually connect this voltage doubler and connect it to the required peripheral. So, these are the typical applications. Now, let us switch to the demonstration and move on from there. What we have here is a microcontroller board, and we have taken a general purpose board. Madhuri has taken a general purpose board here. You see these two devices here, these are essentially capacitors. Diodes are not so clearly visible, but never mind. You may want to look at the multimeter in order to see what is the input and the output voltage. First step what she will do is she will show you the input voltage. Okay. So, just look up this multimeter. So, what you read there is 2.84, right, 85, let us say 2.85. So, we measured 2.9 at that stage, but now it seems to give you 2.9, it is alright, never mind. So, accordingly the output will be a little lower. So, that is 5.2, okay, good. So it is 5.21, alright, very good, excellent. So, you can see that by magic what you will measure at the output indeed is 5.2 volts, and you can simply rig up this circuit and try to drive your peripheral which requires higher voltage. You have to do impedance matching. You have to impedance match, and then you should be able to store the energy, into a capacitor, and use that energy. So, let me draw the picture for you, block diagram. You have the antenna, this is the receiver antenna, there is an impedance matching, then you are feeding it directly to RF DC. This is the Dixon charge pump, Dixon voltage multiplier, I will simply call it dVm, you get output voltage. This is the RF harvested voltage. Use this to drive either through a LDO or directly your load. It is useful to put an LDO all the time, because you will be able to do load isolation. So, let me put a smaller picture. This is the C in, which you know very well, and this is the C out, and this in turn is connected to the microcontroller SOC. Okay. So, this is harvesting in the 850 megahertz. This what I showed you demonstration is BLE, Bluetooth low energy transmission, in the 2.4 gigahertz, right. So, these are some of the experiments we did with respect to the RF DC. It is important now to know literature about RF DC in detail. All right. So, what we will do is, the story is never incomplete if we do not understand everything about the RF harvesting in its completeness, right. So, what are the elements of, so we saw a demonstration of an RFID reader which is working in the sub 1 gigahertz frequency, powering a RFDC system which uses a voltage doubler configuration, and ultimately you are able to send out a BLE transmission packet, right. So, we saw that demonstration and we also saw the circuit topology that goes behind, but if you want to really build a complete system with the RF energy harvesting, there are so many parameters people actually talk you, and lot of literature which actually talks about efficiency of such a system, right. This is a big thing in the RF harvesting domain. So, we have to understand all those aspects correctly. For that, what we will do is we will go through one recently published article and run through that article completely, which is a very good eye opener on all aspects of RF harvesting in the domain related to RF energy harvesting. But before that, I also thought I should show you another demonstration which essentially is a RF energy harvesting chip which we did in the lab, which we built in the lab. Of course, the chip was basically designed in the lab and given out to a foundry process, so that you acquire the bare die, and from there you package the die and then you get the packaged dies. So, the chip fabrication did happen in the lab, because that is a different process and different equipment, factory requirements which fabrication requirements which are there, but the chip was designed here, right, simulated and designed here. So, I will show you a short clip of what we did and go into the detail of that chip and explain to you how you can actually go from a discrete component solution where we use Avago diodes, multi-stage Avago diodes, and then build a system, down to a very small compact small chip which can also do the same functionality, but at a much reduced much at a lower input power level. Also you can also do it at a smaller size. Okay, so let us see that little demo. For that, I will, before I show you the demo, what I want to actually discuss is, I will show you a demo, right. First things, demo of a RF energy harvesting chip. this is the first part. Okay, this chip was built in our department, it was done in joint collaboration with the ECE department, ECE and ESC, DESC actually, Department of Electronic Systems Engineering, together built this chip along with students, right, our own IISc MTech students, Bharat Hegde and Syed Yunus actually built this, designed this chip. So I will show you a demonstration of that. After I demonstrate that chip, the functioning and working of that chip, I will then go into the details of the chip, the internal details of the chip, and then I will then go and look at the literature on RF energy harvesting. These are the 3 things that we should try and see if we can complete. Very good. So first is to run through the chip. So let me open the chip and then we will, yeah, so this is the, so let us play this clip. So first let me start this video. So first is to, okay, so let me restart this video. Okay, so here is a RFID reader that you see here, which is throwing energy RF power on this antenna. This is a quarter wave match, antenna, impedance matching system, and the chip is right here. You see the voltage being read there, right. You see nothing here now, you will quickly see something, yeah, there you see, you get some value, the value of the temperature also has changed. So let me go slowly and re-show this demonstration again to you. You will see that the voltage is slowly building up, it builds to 1.95, at the instant when it builds to 1.95 you will get a data transmission. Okay, so 1.6, 1.7, there you go, slowly it builds, then for a moment you will see that 1.95 and then you will see a packet here, right. So which is clearly what it is doing is it is harvesting RF power, and you can see it is a quite a distance from the antenna here, and the quarter wave impedance matching, then the chip here, and the complete application here. Very good. So, so this chip, what does it contain inside it? What should we, how should we design this chip, and all that I will try and show you a little bit on that front. So to begin with, this chip essentially is was designed by 2 of my students, Syed Yunus and Bharat Hegde, as you can see, guided by ESC faculty, ECE faculty Professor KJ Vinoy and also myself. So this is an RF energy harvesting chip based system. There is one part which is the chip, the other is indeed the complete system that they built. Inside this chip you will see that quarter wave match which we discussed is here, the impedance matching circuit is here, and then what is inside the chip is an RFDC, usual Dixon charge pump that we looked at in the previous times is already here. Then there is a 5 stage DC-DC, it is a boost converter, this is a 5 stage boost converter, and then there is a storage of the energy that is harvested through this, there is a capacitor here. In a nutshell, this is what it contains inside. Getting into detail here, the quarter wave match which is which was actually at the small PCB which was attached to the antenna is here, the RF energy harvesting chip is there. Then there is an LDO which is doing actually it is sort of isolating the load. Recall, I keep telling you that it is important not just look at an LDO from the fact that it is providing you a stable rail, its utility can be many types. In this case we are actually using this LDO for a nice purpose. The purpose is that if you recall the demo, the voltage was building, right, Once it reached a critical of 1.95 and a little over 1.95 volts, you had a packet transmission. Then it dropped to 1.6 volts, recall the demo, alright. You did not make it go to 0, we were not draining it to 0, which clearly indicated this LDO was turning on at a given voltage and powering this complete system down here. This this little CPU, this SOC, which had a BLE interface, and then there was a sensor, and the sensor we used was LMT84, which is basically a temperature sensor. So the function of the LDO is to turn on the system, at a given voltage and turn off also when the voltage drops to a certain critical voltage. This essentially means you are taking care of a certain hysteresis that the you are exploiting, not taking care, you are exploiting the hysteresis which is associated with the LDO turn on, enable and disable, because you do not want to discharge this capacitor completely, you do not want to discharge it to 0. You want to do a packet transmission and then you want to use that energy for packet transmission, and then you want to replenish the energy and therefore keep sending out packet transmissions at regular intervals, right. So you can see that that is possible because we are actually exploiting the LDO's hysteresis associated with the LDO, and in fact the such LDOs are available. So when you talk about design for IoTs, when you talk about system design, when you look at the power supply section, look at the novelty by which you can use this LDO. You can use it as a switch with hysteresis, turns on at some voltage, turns off at some other voltage, turns on again at some voltage, turns off at another volt, again at the same voltage back. This way you can harvest, communicate, compute, sense, whatever, and then replenish the energy by turning it off and then again do the same operation all over again. So that is really the the actual story behind this chip. RFDC, nothing but a voltage doubler, okay, and essentially we are trying to exploit in silicon the fact that you can construct diodes from them. These are all the W/L ratios, you do not have to worry so much about it. The fact that we have optimized the RFDC for a given frequency, this is very critical. When you say you are talking about RFDC for what input frequency becomes important. So all these optimizations inside in silicon are for a given frequency. So the first parameter of anything when you do with RF energy harvesting is that you should know that you are optimizing for a particular frequency, you are optimizing for a particular efficiency, you are optimizing for a given load. These things will keep recurring back to you. Recall what I said in the introduction, you optimize for an application, you optimize for a specific goal. These things are falling in place already when you look at this fact that you will design an RFDC for a given particular frequency. In this case it is the sub 1 gigahertz, and again this is not a very important slide because it gets into detailing on simulations that you have to do. EDA, basically you use some EDA tools like Cadence, Metagraphics and so on, and actually simulate them and see its performance before you actually tape it out, right. So these are all some optimizations, but I want to point out that if you really use diode connected MOSFET, which is shown in this picture here, it actually cuts in much earlier than the regular Schottky diode that you can actually buy. So which means at low powers, at very low input RF input powers, you are able to already start using it very effectively, you are able to rectify very effectively at very low RF inputs already. So essentially it is just conveying that meaning. But what is important is this nice picture here on the left side, which is a clear indicator to say that you will see efficiency which is roughly 30% all through and through. It is starting with something close to 30% and it is trying to maintain the same efficiency over a large range of input powers. The x axis here you can see is the input power, RF input power in dBm, right. You can see that you can feed as low as minus 12 dBm input power which the antenna can take and provide you RFDC, very important note here, RFDC efficiency. It is not the complete system efficiency, I want to stress this, okay. It is not the complete efficiency, it is the RFDC efficiency. The efficiency is close to about 30%. Output voltage that you get is also shown here. It is quite a natural thing, as the input power increases, RF input power increases, the voltage that is developed at the output of RFDC, the DC output voltage that is developed also starts increasing, which is quite natural, right. Which is bringing us to a very important point in the right side of the picture. What is the voltage that I can develop for a given RF input power is already a matter of discussion in the RF energy harvesting world. Many papers that you say, that you read and follow, you will actually understand that they say I can give you this voltage at this input RF power. They keep saying this, alright. So many papers claim what is the output voltage that I can develop for a given input RF power. So please note, efficiency is one part, the second part is what is the output voltage that they can give you for a given RF input power. This brings us back to the same picture here on the right side, which says you can see that it is giving you 1.87 volts at minus 3 dBm. At 0 dBm I get 2.2 volts, okay. Then they say frequency is 915 megahertz and number of stages which they are talking about, the DC-DC stages, DC-DC converter stages is 7. Another paper says I will give you 2.2 at 0 dBm, I will give you efficiency of RFDC efficiency of 6% at 0 dBm, and that is the highest efficiency they are able to achieve, and the frequency is now in the 2.4 gigahertz, okay, and number of stages is 7. Clearly there are advantages of doing on chip implementation of both RFDC as well as DC-DC. What should go in? RF input will go in with a matching circuit. In the demonstration I showed, it is a quarter wave match. You have RFDC, RF antenna with a certain gain, of course, antenna will have a certain small gain, and then you have the quarter wave matching circuit which feeds directly to this chip, and then output you get certain DC output voltage. And now you measure the input to the output, and you say you look at the input the output DC voltage to the input, you take power, for instance, you take output power that you can deliver that you get, and the input power, and you take the ratio and you get the efficiency, power efficiency ratio. These things are done. When we go through that paper we will discuss that in detail, but at the moment this is what you have as a nice picture. Now what is it that went inside the chip? Let me detail this, very important for those of you who are interested in building RF energy harvesting chips. You may want to look at different topologies. Recall I drew a very simple diagram of a voltage doubler and the fact that you need multiple clocks. For each stage you need a clock. Without detailing too much into that, you must need, and importantly you need a clock generator, and you need these non-overlapping clocks to clock each one of the RFDC stages, right, and therefore clock is a very important requirement. But what is also important is the fact that the best known topology for building a DC-DC is indeed this point that is written here, which is the switched capacitor based boost converter. They say from literature that this indeed is one of the best possible topologies you can think of when you want to build DC-DC converters on silicon. Okay, the other best way would be the ones that we know very well from the previous discussions that we did was if you take buck converters, we actually put inductors, right. There is an output inductor at the output, and we also spoke about the inductor current, the picture that I showed there. That is one way of doing it. You can also have inductors on chip, but then they are a lot more harder to achieve, but it is possible. It is not that you can't do without inductors, you can do inductors on chip as well. But from what we see, This is possible that switched capacitors are definitely very high performance circuits, and they essentially are able to provide very high, they are supposed to be the best in topology. This is the key, this is the key here, and we have reached the required 1.95 volt which I mentioned to you by using these 5 stages of DC-DC converter. So you can see that 2 volts from an input of 400 millivolts, okay, minus 12 dBm is the RF input power. You do RF DC, you get 400 millivolt, you take that 400 millivolt, pass it through voltage doubler circuit, you will get 2 volts. Roughly that is what we also saw, a little over 1.95 volts. We started doing the transmission. Alright, so going back to the next slide, here is the clock generator for DC-DC. I will not go into the detail here, and these are essentially the right side picture, that one that you see on top is essentially the amount of area used in silicon for building this chip. But I want to draw your attention to the one on the right side here, where there is input power of -8, -12, -10 and -11 dBm. You will see that the second column is simply the RF DC out. That means after just passing through RF DC you get roughly 0.58 volts for 580 millivolt for an RF input of -8 dBm, and down to about about 410 millivolt for -11 dBm. This is showing you the DC-DC out for different different RF inputs. You can see that it builds as close as 2.8 volts, as high as 2.8 volts. Now you can connect everything well to say that I got 1.96, right, which means the demonstration I showed you was for an RF input of -11 dBm, okay. I gave -11 dBm, and no, not, I did not transmit at -11 dBm. I do not actually care too much about what my transmission power is. What is important is the received power. The input power at the antenna was -11 dBm. It developed 1.96 volts at the output, and DC-DC output, which was sufficient to drive the microcontroller, and that in turn provided me the required power to do a BLE transmission. So this is the key of the whole demonstration, which says that you can also build switched capacitor based DC-DC converters, multi-stage, get reasonable power voltage outputs and use that voltage output for a given application. The application we had in mind was to monitor the ambient temperature, and we had actually interfaced a temperature sensor to our microcontroller, right. So this is the dimicrograph and all that, but let us not worry too much about it. Look at what we did. We used this chip called CC2650, which is essentially an MCU plus radio, and we were actually transmitting BLE broadcasts of the sensor data, as that is what I had shown you on the second mobile phone, which actually read the temperature and a transmission was possible. Quite simple with this little state machine here, a simple flow chart here. Start, if the power is available, after harvesting the MCU boots, and when the MCU microcontroller unit boots, what does it do? It initializes the GPIOs, initializes the call, initializes the tasks, initializes the ADC, because temperatures the temperature sensor is connected to the ADC, and it will wait for reading the ADC. End of conversion, if it happens, you take that, put it into a BLE packet and then do a BLE transmission. All of this is what was actually happening. Fantastic. And again I want to draw your attention to the regular thing that you must be looking at. What is the amount of energy that the system is actually utilizing? So you must know that. So for that, again you do a current, you put a current probe and actually measure the current that the system utilizes. Look at the picture on the left side, you will see that the peak is 16 milliamperes, okay, and a transmission of 3 packets is happening at regular intervals of 200 milliseconds. The right side simply shows an expanded view of this little peak that you see here. this peak actually lasts 5 milliseconds, and you can see that there are packets, multiple packets that are being transmitted, essentially one here and one here, right. These 3 essentially are the 3 broadcast packets which are actually sent out, and there is an interval of 200 milliseconds happening. A simple Android app you build, you can actually measure the ambient temperature using RF energy harvesting, right. So what I have shown you is a complete system that you can build with RF energy harvesting for doing ambient temperature monitoring. Now you may ask, what is the amount of energy required for all these operations? Well, we did these energy calculations again. You see BLE advertising requires 540 microjoules, MCU operations require 400 microjoules. Please note that this also includes the ADC sampling, right. You have to sample the ADC to get the temperature value. Sensors need a very small amount of power, it only requires 7 nanojoules, and you need 940 microjoules in order to complete your operation. So the required capacitor value for voltage tolerance of 0.2 volts is 2 millifarad. You need a 2 millifarad capacitor, right. And we started looking at, okay, if I need a 2 millifarad capacitor, what are the types of capacitors are available? The first one is a supercapacitor from AVX Bestcap, 6.8 millifarad, leakage is 5 microamps at 2 volts. Tantalum capacitor, which is a 3.3 millifarad capacitor, it has 30 microamps at 2 volts, the ones that we chose. And then there is also the ceramic capacitor, which is 470 microfarad, it has 3 microamps at 2 volts. So you must do lot of trade offs between duty cycle and the leakage, and try some combination, and the combination that seemed to work very well for us was to try that, use these ceramic capacitors, put them in parallel and somehow get to very low leakage, yet pull off the required application. So 4 ceramic capacitors in parallel was actually implemented. So this actually shows you the story, a complete story. What you can see on the right side, extreme right, is the impedance matching, post impedance match, that is what we got here. You can see this is the quarter wave match part, and then this is the antenna, receiving antenna. The chip is here embedded inside, the microcontroller MCU unit is here, the BLE chip antenna is here, this is the PCB that we put together, and you can see that quite nicely that whole system seems to be working. It is not that if we, this is a nice story to tell you, but there are issues, right. It is not that everything is hunky dory here, there are issues. What are the issues in this? Look at the third column. Third column says you want to do all of this. I showed you a nice demonstration of a charge build up from 1.6 to 1.95 and going down, because we were trying to exploit the hysteresis LDO which was in place. But if you want to start from 0 volts across the capacitor, the third column actually tells you what is exactly the story here. It requires a minimum of 15 minutes if the reader is placed at some distance, roughly 3 meters. It is not important. What is important is the second column, which is minus 2 dBm, and if the reader is kept at a distance of 5 meters from the system, system that we built, the input power is down to minus 8 dBm. Simple to calculate, just based on Fry's equation one can calculate, or you can also use a USB meter to actually characterize the required power. If time permits, I will show you a demonstration of the USB meter towards the end. And look at the third column, 15 minutes cold start, that means from 0 volts across the capacitor, you keep building, it requires up to about 15 minutes, and if it is 4 meters away from the reader, you need 7 minutes, and 25 minutes in the case it is 5 meters away, the source, RF source is 5 meters away from the reader. And obviously the efficiency is best when there is higher input RF power, you get 2.2 percent efficiency from the chip that we built. So big summary, big story, the system that we showed you can work nicely at -8 dBm RF input power. So it can, of course, the chip alone can work at -12 dBm, can give you 1.8 volts, but sometimes it is not useful to just say something about the chip, but it is always useful and important to say something about the system, and this is the key of the whole of the system building exercise on RF input, RF harvesting circuits. So that is about what I wanted to say about the chip which was built in 180 nanometer and the RF harvesting that we did, and all of the requirements and the study, the literature and all that would be required to build, including a nice demonstration of the whole system. Now let us spend time in understanding the actual way by which literature actually looks at all this. For this I will take a nice paper and run through that paper so that we complete the understanding of the complete system. So if you recall, we showed you the transmission with a RFID reader, and the RFID reader that we were using was this particular one. You can see this is a RFID reader. This is something that is throwing power at transmitting at 25 plus 25 dBm, and we said that for any RF energy harvesting you should know what is, it is not important about what is the transmission power, but at what received power does all this harvesting actually start off, how efficiency, what is the efficiency of the RF DC conversion, what is the efficiency of DC DC, what is the combined efficiency of DC DC as well as RF DC and so on, right. So for that what you should actually do is use this USB, we have a very small basically a power meter, okay, and this is which can be connected to a USB port using the simple cable, and then there is an antenna here. So what you can do perhaps is co-locate this setup along with the receiver electronics, and you can start measuring the received power. There is a very simple GUI which is as shown on this PC here. You can see that this is essentially indicating the received power. The received power, as you can see, is changing from minus, it is going from minus, sometimes minus 17, minus 12 and so on, and it is fluctuating. As you can see, as you go lower, as you go closer and closer, antenna going closer and closer to the transmitting antenna going closer and closer to the receiver, you will see that values can even go up to sometimes even up to plus, right. You can see that indeed it also indicates a transmission power greater than 0 dBm. So essentially this demonstration is to help you to assist you to understand that such power meters are available, simple power meters are available in the market, and you can use these power meters. This is from mini circuits. You can use this power meter and make a measurement of the received power, and this is what ultimately will drive several of the systems, several of the several circuits. By making this measurement you will actually know what is the power at which the system is able to receive, the system is able to basically at what received power the system is able to harvest and convert that harvested energy into useful DC output for driving electronics. So that is the main goal, and just pointing out that how do you calculate in theory the received power. Well, the thing is you can use simple Fry's equation for calculating the received power, and therefore that is a straightforward thing which you can look up and already start using for all paper calculations towards the received power. Now let us move on to another important thing which essentially is on. I mentioned to you that if you really want to sort of so let me pull out the paper that I wanted to share with you on the system here. Yeah, so it is here. So supposing you so just to complete the story, I also mentioned that it is important that we go through a full paper, a recently published paper, and which is sort of summarizes several things which you must note when you are actually sort of working with this. So let me expand this completely so that it is clear to you as well. This paper is on RF energy harvesting with low cost lossy substrate for low power supply design. I will give you the overview. This actually uses FR4. FR4 is a fire retardant level 4 glass epoxy coated substrate. Okay, this is basically the PCB on which this whole system is built. As you know that PCBs use most popular PCB material which for most low power low frequency operations use FR4. FR simply stands for fire retardant 4, okay, and different thicknesses are available. You have 1.6 mm, you have 0.8 laminate and so on, right. Now on top of that is the copper. Copper typically is a coating on top of this glass epoxy and reinforced substrate which essentially will have a thickness of roughly 35 microns. Some people say 35 microns, some people write it as 35 micrometer and so on. So anyway, that is what the thickness of the copper which is on top of it. So he is actually trying to tell us that we have made an RF energy harvesting using FR4 for low power supply system. Now when you say dual band, what are the two bands of interest that they have looked at? They have looked also at 900 megahertz, which is right here, and they have also looked at FM. Okay, normally what happens is in cities you have a number of FM stations which are transmitting quite a few kilowatts of power. So they are looking at how to design a RF energy harvesting circuit using both these frequencies. 900 megahertz is also the frequency at which at least some of the operators seem to offer their GSM services. Some of them now, earlier in fact it used to be mostly 900, but people have the operators have moved away from 900 megahertz and are now using the 1800 megahertz range. But nevertheless BSNL for instance in some of its systems towers still use 900 megahertz for their transmission. So these are the two frequencies which they are choosing for their dual band. They have mentioned some nice numbers here, right. I already mentioned about FR4 substrate, you can leave that. What they are saying is RFDC rectification achieved is 14.49 and 27.44% for 868 and 97.5 megahertz respectively. That is for input power of minus 20 dBm. So they feed minus 20 dBm here in this part, they feed minus 20 dBm, push 990 megahertz, this 88 to 107, right, that is the FM frequency. They push that, they feed 88 to 107 megahertz as an input, 88 to 108 I think it is, yeah it is 88 to 108 megahertz as the input frequency here. At minus 27 dBm is the input power, like typically like what I showed you with the RF meter that here that we just saw. If you get a number which is around minus 27, dBm means that is the RF input power, sorry, minus 20 dBm, that is what the paper says. Minus 20 dBm is the receive P in is minus 20 dBm, and they claim that there is a RFDC efficiency which is 27.44% for 97 and 14 roughly 15%, 14.5% for 868 megahertz input frequency, right. The rectifier was connected to a commercial boost converter. What they have done is they have taken their RFDC output and given it to a commercially available boost converter. Unlike the previous one where we actually connected it to our own chip which had multi-stage switched capacitor system, this indeed uses a commercially available chip which is from TI. I think they use BQ 25504, we will see as we go along, and then give you something at the output. The DC output, the end to end efficiency of the system was calculated to 21% for input power of minus 15 dBm and frequency of 97.5 megahertz despite the use of low cost lossy substrate. This is really the highlight of their measurement. The efficiency is 21% for an end to end system. Please note, end to end meaning RFDC plus DC-DC, which can ultimately be used to either power a microcontroller, an SOC and a sensor and so on. So that is what they are getting around 21% for an input RF, that means P in here is minus 15 dBm. This is for the FM frequency. So this is really this big summary of their paper, but let us look at what this paper says as an exciting way of writing this paper. I like this because the way it has been written, easy to understand, easy to follow and quite easy to connect to this world of RF energy harvesting where lot of results are shown, lot of paper, lot of literature, a very active area of research, but this is what ultimately it matters. You should be able to put up a system from which you can harvest and you can actually drive a complete sensor module or a embedded node or an embedded system or an IoT system. Ultimately that is where the challenge is. So the introduction is quite nice. They talk about Wi-Fi, digital TV and all kinds of RF signals that are available, and wireless power transfer based on far field electromagnetic radiation is recommended for large amount of sensors due to their necessity to become autonomous and self-sustained. See, the nice thing that they write here again is interesting. They say battery replacement is a lengthy and costly procedure in large sensor networks. Therefore, this WPT wireless power transfer concept is suitable for IoT applications such as environmental WSNs and sensor networks for smart cities. Okay, so this is what they claim. On the other hand, ambient RF energy harvesting offers relatively low energy density of a few microwatts per square centimeter. Yeah, this is as I said, these are numbers which are nice to put down in tables and charts, but actual measurements will harvested power will depend on a number of parameters. It will depend on the gain of the antenna, the type of antenna that you use, the environment in which you place, the orientation of the antenna that you end up with which gives you a lot more power, so many other related things. So I would say that you should take this carefully, you should look at this carefully from system to system. Now this next sentence is important. Efficiency is an important parameter in a rectifier topology, that is the ratio of DC output power to the RF input power. Finally you take RF, convert it to RF DC, give it to a DC DC converter, you get DC output rail feed for your sensor node. Please find out what is the efficiency of the complete system, that is what he says, the authors say. Nowadays significant research has been directed towards high efficiency rectifiers. The first stage is important, the first stage rectifiers are important. Many attempts emphasize on the required impedance matching circuit inductances while minimizing reflection coefficient. I am sure you appreciate the S11 requirements such that unless you have a good impedance matching, you will not be able to harvest sufficient amount of power at a given input RF power. at a given input RF power, if you have a claim, that would not work out if you do not do proper impedance matching. This is very critical, right. So he is also saying the same thing, and actually I showed you the quarter wave match that we did for our own chip, and that turned out to be quite successful in trying to harvest at minus 12 dBm and so on. So that is a very critical step. The point is, you should note that just do not connect the antenna and say I am not able to harvest, it will not work unless you do proper impedance matching. So for example, going back and reading it further, for example, RFDC rectification efficiency of 20.5 and 35.3 respectively were observed for minus 20 dBm and minus 10 dBm input power respectively. So he is saying that there is this block of RFDC has different efficiencies based on the input power. Obviously if you feed in minus 10 dBm, much higher power, the efficiency seems to be much better. So let us read it further and look at the whole thing. Before we move on, let me just describe the circuit for you, also well written paper and also a good circuit. You can see P in is here, right, this is the P in. Clearly all of this that I have circled here is all that impedance matching part here. This is the diode, these are the diodes here, and then this is essentially what you get at the output. There are also other components which are modeled in this particular diodes, they have also been accounted for. Ultimately P out comes here, this is nothing but RF DC. P out, when they say, he is just talking about the DC out after the I suppose he is talking about. So we will see this is an interesting observation. So RF, input RF, this is the impedance matching, these are the diodes, and then this is the output. So let us read this paper a little bit to see what exactly he connects as the load. Alright, so he takes FR4 substrate, they try to use a simulation tool. Remember I mentioned to you about simulations as a very important step in all of this. A very popular tool for RF related impedance matching related activity is the ADS. ADS is I forget the name, you can look up, it is called Advanced Design Simulator, or I think it is called Advanced Design Simulator. ADS is a very popular simulator for impedance matching. You can go to Keysight Technologies, which earlier used to be called Agilent Technologies. They have this tool which you can download, request for a license, install a temporary license. If you are a student or a university, there is a nice licensing procedure. Download that tool ADS, download it, install it, and start looking at how to do impedance matching with this software which I mentioned is ADS. So that is another important thing. Here they use a different simulator, they use harmonic balance and momentum solver, which is for most of their simulation. The substrate they have chosen is FR4, and the dielectric constant for FR4 is 4.4, and this is important when they actually simulate. Now this is basically the reflection coefficient. What is the big takeaway from this? The dotted line indicates the simulation, the full connected line indicates the measurement. There are two dips, the deeper the dip the better, right. This is 0, this is minus 30, this is the sweep across the across frequency. So basically they are showing two dips, one dip is at the sub 100 megahertz range, which is the frequency of interest in the FM, this is the dip for the FM, and this is the dip for the sub 1 gigahertz in the 900 megahertz range. So these two dips are what they are claiming is what is the because of their good impedance match, they seem to claim that they get minus 20 less than minus 25 in the case of the FM frequency, and something like minus 18 or minus 19 dBm S11 for in the case of dB I am sorry dB in the case of the 900 megahertz. So this is a very important thing. So you should do this, this is a nice step by step thing that you should really follow in order to when you are doing an RF energy harvesting system. Now the other result of interest is, you see what happens here. This is figure 4. This is a sweep of the input power, which is starting from minus 30 dBm to minus 5 dBm. This is input, okay. This is P in from that circuit that you see. This is for sub 1 gigahertz, this is for the 868 megahertz frequency. They show how as the input power keeps improving, keeps increasing, basically you are tending towards, if you go from here forward you will go towards 0 dBm, right, as you go along this line. The efficiency keeps moving up higher and higher, and they do show that their measurement is quite good. You can see at minus 10 dBm they are getting 30% efficiency for the 900 megahertz. This is figure 4. Now figure 5, let us move on to figure 5. Okay. So this is the same result, but now the frequency, input frequency is 97.5 megahertz. The sweep is input power P in, as you can see, is again starting from minus 30 to minus 5 dBm. As you go along you will get 0 in this direction, and this is again the efficiency. The measurement you can see their claim is quite high at minus 10 dBm, it is roughly 45 or even close to 50% their efficiencies, and the minimum efficiency that they seem to get is less than 10% at minus 30 dBm. You can see that it is directly related to the S11, because they have a very good S11 characteristic minus 25 dBm, they are able to get much better efficiency as well. I suppose you can connect it to the fact that their match at 97.5 megahertz is indeed excellent, even better than that of the sub 1 gigahertz. Anyway, so that is an important useful observation to connect between the efficiency at 97.5 to the actual S11 that we have. Now this is the rectifier efficiency versus frequency for different input power. So here what he is doing is he is sweeping the frequency, right. This is from 0 to 1 gigahertz he is sweeping, and obviously you are trying to look at the efficiency with respect to these frequencies, clearly indicating that the system that they have designed gives you the best efficiency at only 2 frequencies, and that is at that 97.5 and at the 900 megahertz range. This is for different input powers. You can see that minus 10 is indicated, minus 20 and minus 30 dBm is indicated. So you can look up these nice little charts that you have to make after you build your system in order to actually arrive at something useful, whether it is a useful power or whether this is really useful for building your IoT, for powering your IoT using RF energy harvesting. Right. Now as coming to the simple steps that they try to go about in their characterization, the first goal of modeling and simulation was to maximization of RFDC. This is the RFDC, P out by P in. They just substitute the power that they are feeding in to the RL, which is the load resistor here. So I suppose when they mean RL they mean this system here. So this is surely the efficiency of the RFDC system, output of the RFDC, which is what they connect here. So this is another important thing, keep note of this resistor here. Essentially when you do VI characterization of a solar panel, or you do VI characterization, that is voltage and current characterization of either a solar panel or that of a thermoelectric generator or that of a linear motion harvester, and now that of a RF energy harvester, often you have to do the you basically plot the VI characteristic, right. Quite like that, this is also the same story here, that you do you basically so the point I am trying to say is, for any of these characterizations what they normally do is they connect an output resistor and they keep changing this resistor value. They put a potentiometer at the output here and keep changing the potentiometer value till you obtain the maximum V and the maximum I, and then you plot, right. This is a standard way of characterizing the panel by putting a potentiometer here. Quite like that, this experiment is also done in the same way. They have connected a resistor here, a variable resistor here, and potentiometer here, and they keep modifying the changing the value to get the efficiency. So now RFDC efficiency is P out by P in. This is the reflection coefficient, which is also quite straightforward. You have for input power of P in of -20 dBm at 868 and 97.5 megahertz. The input impedance Z in is given by V in by I in. Pretty straightforward set of equations which you can actually follow quite easily, and how they do the match. So according to, so let us read that part, which is a very important thing here. So you can say that the load at the output RL was fixed at 9.2, they show 8.2 there, but I suppose they have put a 9.2 k ohm as well as also tried it with the 9.2. Measurements were employed after that using a signal generator and a voltmeter. You can see these are simple equipment. The simulated and measured reflection coefficient was shown in the S11 was shown in figure 3. Reasonable agreement is there between the predicted and the measured results. Figures 4 and 5 depict efficiency versus P in and all that. So according to measured results, the efficiency is 14.49 and 27.44% at 868 megahertz and 97.5 megahertz respectively for P in of -20 dBm. In other words, what he is saying is that if you feed P in of -20, the input power is -20 dBm, you will see about 14.5% and 27.5% at these two frequencies. That is what the ultimate story is. So you have to do these characterizations before you can actually use anything. What is the required input power to drive my system if you want to know, what is the duty cycle of the node you want to drive, so that you have continuous monitoring if you want to know. Unless you know what is the input power and what is the output power and what kind of efficiencies you get, you will not be able to actually build a successful perennially monitored RF energy harvesting node. So that is the key thing. So moving on, for P in of -20 dBm, the results are 29.64% and 46.58% respectively. Again he claims about his the simulation results agreeing well with the measured results. So antenna design, well, that is another story altogether. You must go through a proper tool in order to actually design your antenna for the application, and this is basically, the design is a variation of a monopole antenna with a loop, and he is talking about the antenna loop, which is right exactly like this. This antenna is the antenna which is working both for the 97.5 and the 868 megahertz. In fact they have chosen 868. This is the antenna that they have actually designed. Now there are further results to know in this paper, so let us quickly spend time here. This is the rectifier efficiency for different output loads. Okay, this is important. I told you about the potentiometer and all that. Before they arrived at anything useful in terms of what is the best value of the load that they can apply, they could not have found out if they had not had a potentiometer and varying the value of the potentiometer such that they get a peak, right. Peak power is got exactly at 1 or at around a, let us say, a spot resistor value. How to get to that? You have to do this. What you do, you start with 0, go on sweeping the load resistor, you can see 0, 10, 20, 40, 30, 40, 50 kilo ohms. You find out the efficiency, go on plotting what you get. For minus 10 dBm what do you get, for minus 20 if the input power is minus 10 dBm what do you get, minus 20, minus 30 and so on, and then you know that you are actually peaking around this less than 10k, around this value is what seemed to work the best. That knee point, this knee point, exactly the knee point here will actually tell you that this is the best resistor load value for getting the maximum efficiency of the system. Now coming to, this is basically the RFDC, please note this is all RFDC part. Now this is figure 7, so let us do it structure, and this is figure 8, and you do the same by changing the input frequency to the FM frequency 97.5, and again you find that it has shifted not so much, right, it is around the same point here close to 10k. So that seems to be a nice thing that for both the frequencies they seem to get around that 10k value, which seems to be giving them the best or the maximum efficiency. So that is about figure 8 and figure 9 now. Figure 9 is another interesting thing. What they do is they sweep the input power, and what they do is they look at the rectifier output open circuit voltage for both the systems. They just say that what is the output voltage that I can get, right, and that appears that they sweep again the input frequency, the input power for the two frequencies, and then they show you that, see, this is what ultimately will determine the usefulness of the system, right, at what is the V out that you should get from your rectifier before you connect it to any standard DC-DC converter. They have not even spoken about the DC-DC converter yet, please note. All the results and measurements they have shown is how good is my RFDC, full characterization of RFDC, all kinds of measurements with respect to sweeping the input power, sweeping the two frequencies, connecting different load resistors, trying to find out where is the best efficiency, all of that is for the RFDC system. So the next story will really be around the DC-DC converter. You can see now the boost converter comes into picture, and they say that we use BQ 25504, which is a standard boost converter from TI. Essentially it seems to be the one that they seem to have interfaced, and ultimately they show that they have connected at the output of the boost converter, they have actually connected an LED. Okay, I will show you that result, I will show you the circuit diagram. So what they do is, this is the circuit diagram here. So what they do, they take the V open circuit voltage and they connect it to this V in DC of so this is the input voltage which is coming into the BQ 25504. It boosts, it starts charging this 100 microfarad at the output, and once the output rail is fine, is stable, this series pass transistor conducts, this LED switches on and it switches off soon after the energy across this 100 microfarad lowers, and then this transistor simply shuts down. So you will have a light on and you will have a light off, light on and a light off, right, essentially that is what their load is. And they use two transistors here at the output. One is the series pass, which is a P channel MOSFET, and an N channel MOSFET for providing the gate trigger. So this circuit you can try, take the RFDC which they have implemented, connect it directly to a commercially available BQ 25504, you should be able to essentially be able to harvest and drive this LED based on RF using the RF input power, alright. So the story really is, if you look at the okay, so I think before we go on there, let me show you the end to end efficiency that they have achieved. after having done this the RFDC, they have to also finally calculate the end to end efficiency. This is a very simple expression, you can see this is energy efficiency, basically total N total, EDC is the energy DC, right, and this is the energy input. Here you are not looking at power, but you are looking at energy. Therefore, the denominator is simply the on cycle 0 to the t cycle time over which the capacitor charges for the input power P in, which comes in the denominator, and this is simply half CV square. You start with a high voltage charge a capacitor building up, and then when the capacitor builds up you switch on the series pass, and then the LED is switched on, and after it the capacitor starts discharging, you go to a lower voltage, and so essentially if you do half C V2 square minus V1 square, VH square or V square high minus V square low, you should get the output energy, quite simple, half CV square here, and this is the time integral of input power from 0 to the time it takes to charge the capacitor. So in essence this is what the explanation here is. So let us read this together and then summarize this nice RF energy harvesting circuit. Okay. So minimum cold start, see this is another thing, self starting, cold starting, all these are very critical in energy harvesting applications. Minimum cold start voltage and typical input power for BQ, this is now all the stories around what BQ requires as an input. This is 330 millivolt and 10 microwatt respectively. Only if it gets this much power, 10 microwatt of power, it can actually not start. Okay. It also has an ultra low power input power levels with low quiescent current, 330 nanoamperes is minimum required. So this together essentially is so you program the resistors for the BQ, it is a standard circuit which you can implement, and the LED that they connect outside requires 20 milliamperes, and the capacitor charges to a voltage, high voltage of 2.82 and the low voltage is 1.63. So you start with 2.82, you switch on the LED, if it goes, the capacitor starts discharging, goes to 1.63, switch off the LED gets switched off because the transistors turn off, and then the capacitor is again charging from 1.63 to 2.82, and that charge discharge keeps going periodically. When the minimum voltage V low is reached, the boost converter and MPPT start to operate, and charge discharge at the load begins, causing LED to flash. The charge discharge operation of the LED can be observed in figure 14 from the boosted signal VBAT. Using the converter topology of figure 13 and DAQ for capturing the signals, basically a piece of equipment, we exported the rectifier output voltage V in DC and the boost converter output VBAT for 800 seconds. Essentially it is a time trace for 800 seconds. The rectifier P in was at minus 15 dBm at 97.5 megahertz. Finally it is noted that the boost converter was self started with no external energy that was used. So it goes back to what we discussed, that energy harvesting, any challenge in energy harvesting means it should be really self starting. This is in summary the whole story of this paper, which is quite well written in my opinion. They also do the end to end efficiency calculation, and they find that they get a 21% end to end efficiency, that is both RFDC as well as DC-DC, because they use a commercially available boost converter like TI's BQ25504. Big summary, if you want to do RFDC, you want to use RF as an input harvesting source, do proper characterization, know what is the input power, power in is important, do proper impedance matching. How do you measure input power? I showed you a demonstration, that you must use a proper equipment. You must be able to measure the input power using a simple power meter. There are cheaper ones available. You can buy some good equipment, cheap ones, accurate ones for your simple applications. Use that for measuring input power, do proper impedance matching, characterize S11, right. Then use necessary diodes for rectification, connect different loads, do VI characterization, find out the right kind of load that would be required to drive your system, find out the open circuit voltage, see what you can do with the open circuit voltage such that it can be fed to a boost converter. You can use any commercially available boost converter like BQ 25504 or any of the Maxim chips or any of the linear technology chips or any one of them, and see if you can build a simple nice circuit which can use the ambient RF around you. This is the big story. Thank you very much.